Screen is visible.
Yeah. Okay. Okay. So, good afternoon, everyone, and very happy New Year. Hope all of you have a prosperous and a good New Year. Uh, this uh, uh, this is a tutorial session. So, although I have something on the screen, it's only as a sort of a background. Most of the time, I would like it to be a more interactive session. So, maybe I will pose some questions, and it would be good if people can sort of respond to those questions. So just to introduce myself, my name is Bhalchandra Joshi, and I work here at National Center for Radio Astrophysics. And my primary research interest is radio astronomy instrumentation and radio pulsar astronomy. Okay, so I guess you have had previous lectures on radio astronomy techniques, on astronomy in general and radio astronomy in particular. But one of the things which would be sort of nice to fix in our minds is how do we actually locate astronomical object in the sky? So I would start by asking this question. Maybe somebody can sort of answer. How do you identify and locate uh, a star or a galaxy or a nebula or any of the astronomical objects that we want to study in the sky? Can anyone answer?
So in case you are measuring it in a particular frequency band, you'll expect like around that star, you'll expect a Gaussian peak or something like that, which tells you that there's an object there.
Yeah, no, you're right. What I wanted to see, for example, if you want to say that, if you want to specify where I am located, you will say I'm located in Pune, which is one way of locating me. But then you don't know where Pune is, so you will say it is in India. Okay, and that's another way of locating it. But again, you don't know where India is, so then you would sort of give some kind of a latitude or longitude for the city.
Okay. Yeah,
That
yeah,
sort of fixes it. So I meant in that sense. How do you locate a star in the sky?
yeah. You have like
Array and deck, array and deck
Array
of
and deck. What is array? What is the full form of array and what is the full form of deck?
Right accession and declination.
So how do you measure the right ascension and declination? Okay. So these are like two coordinates, right? So like latitude and longitude on the surface of the earth, right ascension and declination are also two coordinates. Can anyone name other coordinates which you come across in science, physics? Things which you come across, yeah.
Altitude, azimuth, depends
Okay,
which coordinate system we are looking at.
okay. So how do you define the altitude, for example? So if I say that a star is at an altitude of 40 degrees, what do I mean?
It has an elevation angle from the horizon, 40 degrees.
From the
Right.
reference circle.
Right. So for any coordinate system, you need a reference plane. Okay. So the most simple coordinate system which all of you have come across even in school in 10th and 12th standards is the Euclidean coordinate system, the XYZ coordinate system. Okay. So how do you define X coordinate? You define it with respect to a plane, which is the YZ plane. It's basically the distance from the YZ plane. So that's what is actually the way you define a coordinate system. Let me try and see if I can go to the next slide. Okay, so this is your normal XYZ system. Okay, so what is the Z coordinate? Z coordinate is just, if you see the place where my cursor is, Z coordinate is just the distance from the XY plane. So the XY plane is the reference, and the distance from the reference is the actual coordinate. So that is how the Cartesian coordinate system is defined. which all of you are very well familiar with. Okay. So now somebody mentioned altitude azimuth, and I asked, how do you define altitude azimuth? So we have already got one definition. So what is the reference plane for altitude?
The horizon plane.
Right. And
Local horizon.
Horizon.
no. Yeah. So whoever said local horizon is more closer to the. So how do you define horizon, right? So is the horizon same in Srinagar, same in Tirunelveli, and same in Pune?
No.
No.
No, different.
Yeah,
So
that's why altitude depends on location.
correct.
The latitude of the observer.
Right. So that's an important point to keep in mind. What about the other one, the azimuth?
Azimuth north reference frame.
No, as I said, for any coordinate system, you have to define a plane. Okay. Now, horizon is a plane. It's the, if you extend your line of sight in all directions, that whole plane is the horizon plane. So you need a similar plane for azimuth. So you're right. North has something to do with it, but
The meridian, North Pole, South Pole, and the. But if we connect a line, so zenith, North Pole,
right.
true north.
Correct. So this alt azimuth system is called as horizon system, and you are correct. So zenith is, so if you, let's say this is a representation of the place you are in. So you are the observer at the center of the sphere. Okay. This big plane is your horizon plane, which is the shaded plane. So any angle from the horizon plane along any great circle in this sphere is called the altitude, which somebody already defined. Okay. Now you need to define the other plane. So you need some, to define a plane, you would need some points. One direction is not sufficient. So somebody said north, so fine. So north is one point where my cursor is pointing. You need another point to define the plane. Okay. So, and you need that point to be unique. So zenith is a point which is right above your head, and that that point is then sort of called is called zenith, and a plane which contains both zenith and north is your reference plane for azimuth. So any angle from this would be your azimuth coordinate, and you go from north to east direction. Okay, so again, you have to define a direction, right? What is positive and what is negative. So all positive angles will be towards the east. So this is typically the alt azimuth coordinate system which we are discussing. Okay. Now this coordinate system has some problems. Can anyone tell me what problems this coordinate system will suffer for use?
Depends on location,
Depends on the location of
time,
the observer.
time
Yeah.
also.
Okay, that is true. How does it depend on time?
Because of Earth's rotation, our horizon
Rotation
plane
of
is also
Earth.
changing.
Yeah.
So the
Correct.
coordinates of a
Correct.
particular star would change.
Fine. So if there are three astronomers and one of the astronomers has discovered a star and he wants to tell the other two astronomers who are not in the same geographical location, say let's say the astronomer who's discovered a star is me in Pune, and I want to tell somebody in Australia and tell somebody in US. Okay. So if I give alt azimuth of the star, they will not be able to locate it, right? Because the altitude keeps changing. The stars rises and sets because of the Earth rotation, as somebody correctly pointed out. And so does the azimuth. It also keeps changing as the star rises and sets. So this is the basic deficiency of this coordinate system. And you don't directly use this system. So then how do you take care of this?
With area and deck coordinates.
Okay, so what is the difference in RA and deck versus this? Why is RA and deck not time and location dependent?
Because we consider the celestial sphere there, and that's kind of a constant.
Meaning the reference circle is the equatorial plane, celestial equator.
And equinox.
Okay. So, so now we have come to that celestial system. This is also called as equatorial coordinate system, as somebody was pointing it out. Okay. So how do you form this coordinate system? So your Earth is somewhere in the center where my cursor is. Okay. So how do you form this coordinate system? So again, you have to define two reference planes, and one reference plane somebody defined, but the other plane is yet not defined. Okay.
That is
You,
elliptic.
Path of the sun,
uh,
and starting from the vernal equinox.
path of the sun.
Yeah. Isn't it right?
No. See, you have to define. See, when we started, I said that the coordinate systems are defined by a reference plane. So if you want to define your right ascension and declination, you have to first define the planes with respect to which you are going to measure them. So which are the planes?
The first plane is directly parallel to the Earth's equator,
Right.
and we then take the elliptic, which is the path of the sun. So it
No.
intersects.
Go
in
one
two
by one.
points.
Go one by one. So you are right that the first reference plane is the plane. If you extend the Earth's equatorial plane, okay, and take it all the way to an imaginary sphere around the Earth, which is known as celestial sphere. This plane is the reference plane for which coordinate?
This is for
Declination.
declination.
So all the angles above this reference plane, right up to North Pole, are plus declination, and all the angles below this plane are minus declination. Okay, so you define declination. Now let's come to the other one, which is the right ascension. So what is the reference plane for right ascension?
North celestial pole and vernal equinox connected by
A great circle, right? Correct. So if you take the north celestial pole, south celestial pole, and vernal, so what is vernal equinox?
where the celestial equator and Earth, no, celestial equator and the path of the sun intersect.
Correct. Ecliptic. Path of the sun is called ecliptic.
Yeah.
So there is a plane, it defines a plane. So there is an ecliptic plane and there is an equatorial plane. Where they intersect is an equinox. Okay, but there are two equinoxes. So which one is vernal equinox? Well, this does not uniquely define it.
The March equinox.
Yeah.
March equinox. Okay. So March equinox. Now, if you have a source which has a right ascension of 0, okay, where will you see it on the sky on, say, March equinox? When is the March equinox, by the way? Can somebody tell?
21st, 22nd March.
21st March.
Okay, so on 21st of March, where will be the 0 right ascension star? So if a
Just
star has,
rising above east sky.
It would be at 0 RA 0 deck.
it will be at 0 RA 0 deck. No, but how do you define 0 RA 0 deck? That is okay. Before we come to that, the reason why we went to this equatorial coordinate system was that we didn't want it to be time and place dependent. So why is this not time and place dependent? And whether this statement is strictly true. So can anyone hazard a guess?
It would be true for an observer on the, like strictly speaking, it would be true for an observer on Earth only. Like You're observing.
Yeah, no, we are still talking of everybody on the Earth. We have not gone
Then
to extrasolar planets. So we are still talking about everything on the Earth. So, but why is it time and place independent for an observer on the Earth?
Sir, probably some reference is defined, like reference frame is defined through which we are going to measure the value.
No, that was done for the altitude system also, right? You had two reference planes, and you sort of measured the coordinates with respect to that.
I guess another requirement is that this time that we're talking about March 21 and all, that should be like a generalized time. It should be true, like for example, GPS time or something like that. If it's like the observer's local time, then that won't work.
Yeah, some part of what you said is correct, but that's not the reason.
So actually, I think it's like when the sun on the
Dependent
21st
of
and
Earth's
22nd
rotation
March
and revolution.
comes actually intersects with the east-west plane. That's where we call the vernal equinox, and that's constant for all over the globe actually. Whatever we say so, because 21st the time is the constant
Right.
21st to
No,
22nd.
so one thing which you said is correct, that the vernal equinox is a uniquely defined point, and it is the same for everybody. It is the same in Kolkata, it is the same in Bhopal, it is the same in Pune, it is the same in New York, it is the same in London. Okay. So it does not depend on where you are, right?
Yes, sir.
Okay. What about the equatorial plane? Does it depend on where you are?
No, sir, it does not depend now because
Correct.
it's a perpendicular to north south. So
Correct. Correct. So neither of these two planes, that is the reference plane for right ascension and the reference plane for declination, are dependent on where you are located on the Earth, right? So it is independent of the location of the observer, which was not the case for the horizon system. In horizon system, the planes depended on where you are. The same is true about time dependence. It does not matter. The celestial equator will remain where it is. As the Earth is rotating, it's not going to change the celestial equator. It's neither going to change the first point of Aries, right? Because both these planes have been defined in a time independent way. So that is why when you use a equatorial coordinate system or right ascension or declination, you uniquely define the position of the star. So now in Pune, if I have discovered a star and I want to communicate it to my colleague in Australia or in New York, okay, or say in West Virginia, it would be very easy for me to do because I'll just give right ascension and declination, which is place and time independent, and my colleagues will understand uniquely where the star is. They will look at the star and say, yeah, correct, you have discovered a new thing, right? So it's very important to understand these coordinate systems, okay? But radio telescopes, we are in a radio astronomy winter school, so I will now sort of relate whatever we have learned till now to the radio telescopes. So radio telescopes are very large entities. What are the typical sizes of radio telescope? Can somebody tell us?
Tens or hundreds of meters in diameter.
Correct, correct. And a typical optical telescope like the one which you might have used to look at the conjunction of Saturn and Jupiter 10 days back. What is the size of that optical telescope?
A few inches.
Yeah, few inches. So unlike
1.5
optical,
to 2 inches.
in fact, the largest optical telescopes are in meters. Okay, they are not very, very large, whereas typical radio telescopes are in tens of meters. Okay, so radio telescopes are very large structures. Does anyone know how big is GMRT, Giant Meter Wave Radio Telescope?
45 meters.
Right. So it's 45 meters. Good. I'm happy to hear that at least somebody knows how big is GMRT. So it's, as you can see, a typical radio telescope is very, very large compared to optical telescopes. So you cannot sort of use the equatorial coordinate system directly. You mount the radio telescope in what is known as altitude azimuth mount or in the horizon system. Okay. So the coordinates which a radio telescope follows to point to any direction in the sky are horizon coordinates. Okay. Now, stars are specified in equatorial coordinates, but to look at them, you need to go to the horizon coordinate systems. Okay. So how do you sort of resolve this dilemma? Any guesses?
Coordinate transformation.
Coordinate transformation. Okay, good. So, okay. So, but before maybe I can directly go to that. So this is the typical coordinate transformation, which is there. Okay. And that also makes it clear that the horizon system is time and place dependent. Okay. So if you look at that on the left-hand side, you have the altitude and the azimuth, okay, or sine and cosine of altitude and azimuth. On the right-hand side, you have the declination and a quantity called hour angle, which is related to right ascension. We will come to what is hour angle. You can for the time being, assume that hour angle is a proxy for right ascension. Okay. So the declination and right ascension is on the right-hand side, but you see that these things are multiplied by latitude, as well as in the hour angle, there is a time dependence. Okay. So the altitude azimuth automatically, as a result of these expressions, you can directly see that the altitude azimuth is both place as well as time dependent. Place dependent because latitude has entered here, and time dependent because hour angle is a function of time. Okay. So by definition, these two coordinates will be place and time dependent. And you use the place and time independent coordinate system, the equatorial system, on the right hand side to do this kind of a conversion. And then you position your telescope in altitude and azimuth, and that is how you can uniquely locate that. Okay. So I hope this is all clear to everybody. Is that, or maybe I'll ask that a little later. But in this, we also need to sort of learn a little bit about astronomical time. Okay, so let's come back here. So the time as we in your watches. Okay, so right now it's about 2:30. So what is this time? When you say that it is 2:30 in the afternoon, what do you mean by that? Indian Standard Time or Greenwich Mean Time? What kind of time is this?
IST.
Indian Standard Time.
Yeah.
It's a IST, but how do you measure this time?
Based on the motion of sun, solar time.
Okay. So one day is, how do you define a day?
From fixed time to back to that fixed time, 24-hour cycle.
Right. So what is that fixed time? Okay.
Actually, it is a solar day, so the time for which the sun just go rounds back and comes to the celestial point again.
Right. You need a unique point. I agree that it is, since our time is dependent on the rotation of the Earth, and the rotation of the Earth is 24 hours. So so that's how the sun would come to the same place there. But which point of the day you measure the time?
Overhead, when the sun is overhead.
Right. When the sun is crossing a circle known as your meridian circle. Okay. Which is, so if you look at this, if you connect south, north, and the top of your head, that circle is called as meridional circle. Or if you look at this, this is even better. So north, zenith, and south, this is called the meridian circle. Okay. We know that all stars, including sun, they rise in east and then they set in west. So there will be a point of time when it will cross this south, zenith, north circle or the meridian circle. That crossing of the meridian circle is known as transit. So the jargon for that is that the star is transiting or the sun is transiting. Okay. So when does the sun transit the meridian circle?
Noon.
12 noon.
So our clocks are set to measurement of time in which a day is defined as time elapsed from one noon to another noon. That is the strict definition of the day. Okay? And then you divide it by 24 times, that becomes 24 hours, and then divide it by 60 times, that becomes 1 minute, divided by 60 again, and that becomes 1 second. Okay? So that is how our civil time is defined. But this has a problem for astronomy. Can somebody tell me what why this time is not useful for astronomy?
Side real time is there.
What is side real time? Correct.
And another extra angle that has been covered by Earth due to revolution around the sun.
Right. Okay. So just to look at that, if we look at this, so what is happening is the sun is not stationary in the sky, right? And that all of you must have noticed that in summers, the sun is almost overhead at noon. But right now, around December, where do you see the sun? Do you see the sun overhead or you see it somewhere else?
It's shifted southwards,
Somewhere else.
much southwards.
It's shifted southwards. So why has it shifted southwards?
Because of the revolution of the earth around it. Like now, so we're in the northern hemisphere of the earth, so like now it's facing away from the sun, like tilted backwards a little, so that's why it's shifted a little southwards from our
Basically because of the tilt of the earth's axis with respect to a line perpendicular to the ecliptic, okay, or the path of the sun. Okay. So there is a 23.5 degree tilt between the two. That is the main reason. But what does it do to the coordinate of the sun? See, like every star, sun should also have a right ascension and declination, right? So what is the declination of the sun as of today, roughly, approximately?
About minus 22 degrees south, because we had 1 week ago the winter equinox, winter solstice.
Right. So at winter solstice, the sun is the most southernmost. And so it is, if you look at my cursor here, it is somewhere here. Okay. So it is 23.5 degrees south of that. Okay. In the summer solstice, what would be the declination of the sun?
Positive 23.
Right. And during the equinox, what is the declination of the sun?
0, 0.
0, 0. So you see that unlike stars, the declination of the sun changes throughout the year. Right?
Yeah.
Do you agree with me or not?
Yes, it changes.
Actually, the declination of not only the sun changes, but the planets also change. And in fact, the declination of Saturn and Jupiter was almost the same, except for a 0.1 degree separation between them. It was almost the same on the winter solstice on December 21st. I don't know. Did you guys watch the conjunction on 21st of December?
Yes.
Yes,
Yes.
yes.
Yeah.
Yes, sir.
So that's the time when Saturn and Jupiter had exactly the same declination and the same right ascension. Okay. So planets, the solar system bodies, the right ascension and declination changes. That also tells you that the right ascension declination system is not based on solar system bodies. It is based on faraway stars. Right? Because if it was based on solar system bodies, why would the coordinates of the solar system body change? The very fact that the coordinates change means that this system is basically based on faraway stars, which are unchanging. Okay. So, if you use the time which is defined by sun's motion, that will make some complication in finding out stars, right? So then what time should you use?
Star time, sidereal time.
Okay. So how do you define a sidereal day? Right. Star time is called sidereal time. So how do you define a sidereal day?
So when it is a distant star is overhead, same as we did for sun.
Correct. So if you take any star and you say, ki, well, this star when it transits today and when it transits tomorrow, the difference between that is what I will call as a sidereal.
Sidereal
So,
day.
so that is a sidereal day. How? What is the relation between the sidereal day and a solar day?
The sidereal day is shorter by 4 minutes.
Why is it shorter by 4 minutes?
Earth motion because of.
So can somebody do that calculation quickly? Show that it is shorter than 4 minutes. You don't need to do the full calculation. You can just indicate what you will do. Okay. And do the calculation as an exercise. Well, how would you find out that it is shorter?
Whenever we had a 360-degree rotation, we had the 24 hours, means 24 into 60 minutes. So now we are having a 1 degree less approximately.
Why you are having 1 degree less?
Because the Earth's tilt, Earth's equinox has been shifted a bit from the Sun's center and Earth's center. Not equinox exactly. Line of center has been tilted a bit.
That is not something. Well, is first of all, equinox is fixed. It is not moving anywhere. Okay, it's remaining where it is. Something is moving, and something is moving by roughly 1 degree. But what is that something?
It is the Earth which is moving around the sun. So it is moving like 365 days. So per day it is approximately 1 degree.
Correct.
Now the Earth is moving in such a way that the sidereal times become short of 4 minutes. Had it revolved in the other way, we would have 4 minutes
No. So
longer.
you have whatever you have said till now is correct. That there is a 1 degree difference every day. Okay. And so how much is 1 degree corresponding to? Now you have to tie that to 4 minutes.
So it's basically 1 by 360 into 24 into 60.
So 1440 divided by 360 is 4.
Correct. Okay, so you can do this calculation correctly. Actually, the difference is slightly more. We did a very rough calculation. The difference is 3 minutes 56 seconds. Okay, so that's what is written here. One sidereal day is smaller than solar day by 3 minutes and 56 seconds. Okay. Now, what is the consequence of that? The consequence of that is that your sidereal time and the solar time are not going to be synchronized, right? They will shift with respect to each other. So if you want to observe a particular star at its transit, that transit will happen every day at a different point of time, right? So that needs to be accounted for. And the way it is accounted for is by saying that by defining a coordinate called hour angle. Okay. And this hour angle, which is written here, this hour angle is related to the sidereal time. Okay. Now, as we defined, the sidereal time is nothing but a sidereal day divided by so many 24 hours. We need some zero for that, right? Now, the zero for that is simple to define because the right ascension zero, which is the first point of Aries, when it transits, you call that as the 0 hour of the sidereal time. Okay. Now, any star which is far away from this 0 hour transit, okay, it's very easy to figure out when it will transit. So, for example, a star at a right ascension of 8 hours, okay, means that if currently the first point of Aries is transiting, this star will transit 8 hours later because the right ascension is simply linked with the sidereal time. So in other words, the sidereal time at a given place, say for example in Pune or from at Delhi or Chennai, is basically the time, is basically the right ascension of the star which is transiting at any given point of time. That is the sidereal time. Okay. And if you know the right ascension of the star and you know the sidereal time, the difference between the two is called as hour angle, which can be negative or positive. And as the earth rotates, the hour angle is going to change. So we have implicitly put the time in the hour angle, and that is what goes in these coordinate transformations here to get the altitude and azimuth. Okay. So I hope I have explained the coordinate systems to some reasonable degree. Are there any questions before I move to something else?
Sir, Earth's tilt doesn't change this a bit after a few years, like by
That's a good point which you have raised. So we assume that the right ascension and the declination, that is the equatorial system, is a constant system. Okay, but as you pointed out, this is an assumption. So what is the variation? Can anyone say? And why is it there?
Elliptical path.
after searching on it, I'm getting that in 40,000 years it has been changed from 22.1 degree to 24.5 degree. It is varying between those values.
What is varying between which values?
Earth tilt axis from 23.5 degrees is been set at present, but it has been varying from 22.1 to 24.5 degrees.
So why does it vary?
The tilt rotation axis has been changed. So,
Because of the precession of Earth.
Right. So Earth is
yes.
a rotating body, but just like a top, if you have played with a top, the axis of the top actually moves around, and that movement is called as precession. Okay. What's the time scale of precession?
24,000 years.
Right. So it's a very slow change in the axis, but because the axis is changing, your uh, equatorial plane is shifting, and that will change your first point of Aries also. So your right ascension and declination will change as a function of time. Very small amount, few seconds of arc or few minutes of arc, but they will change. So if you want to be very accurate, which you want to be because there are thousands and millions of sources in the sky, then you will have to tell that your right ascension and declination has to be defined in some particular year. So International Astronomical Union has defined 2 years to define coordinate systems. The earlier one was defined as 1950. So those are called as B coordinates, or the 1950 equatorial or FK4 coordinate system. But from 1950 to today, 2020, almost 70 years have elapsed. And although this effect is very small, it does lead to a substantial shift in coordinates of the right ascension and declination coordinates. So in order to minimize that, the International Astronomical Union in 1990s decided a new year for defining RA and DEC, and that is the year 2000. Okay. And this is known as J coordinates. Okay. So there are these B and J coordinates which you will come across in astronomy in general and in radio astronomy in particular. And just remember they are there because of these small rotational problems which the earth goes around. Okay. So precession is not the only effect. There is another effect called nutation, which also leads to this. It's much smaller than this entire thing. Okay. Any other questions?
Sir, do we assume that the rotation of faraway objects is negligible because we consider like fixed area and deck for those objects? So like, is it negligible?
It is negligible for all practical purposes, but The eventual coordinate system, the real coordinate system, if you want to have, which is completely unchanging, is defined in terms of what is known as quasars or quasi-stellar radio objects. Okay, I don't know whether you have had a lecture on extragalactic objects, but these are powerful galaxies which are at the edge of the universe. Okay, so they are the farthest objects which you can see, and so that system it defines coordinate systems, and that is known as a ICRF coordinate system. Okay, it's not of so much of great consequence as far as the astronomy, day-to-day astronomy is concerned. But yes, if you want to find out motions of objects, motions of galaxies and so on, which is known as proper motion, then you have to take this into account.
Okay.
So effectively, everything in the universe is moving. Okay, it's a question of relative scale of that. So if you look at sun, it is moving very fast. If you look at moon, sun and moon, for example, sun not so much, but moon certainly. If you look at moon today, tomorrow, day after tomorrow, you will really see it moving. Okay, sun to a lesser extent, and other planets to even lesser extent. But once you start going to stars in our galaxy, you already don't notice. They are almost like constants. Okay, and quasars are so far away objects that they are literally constants. But there are precision experiments where you need to consider a different coordinate system. Okay. So other than equatorial and horizon coordinate system, there is also a coordinate system called galactic coordinate system, which is based on the Milky Way galaxy. Again, the reference planes are the plane of the galaxy, because we know that Milky Way is a spiral galaxy. It's a planar galaxy. So the plane of the galaxy is the galactic latitude, and then again the line joining sun and earth defines line joining sun and the center of galaxy defines a plane, which is the plane of reference for galactic longitude. Okay, so many times when you are defining galactic objects, you use the galactic coordinate system. So there are other coordinate systems also which are employed. It all depends on the context in which you want to use these coordinates. Okay, so if no further question, then I will probably continue a little bit more before we get into uh, the pulsar part of it, which is what I was
Sir,
supposed to
I
talk. Yeah.
have a question. Sir, why do we bother like defining the time with respect to like the sun or these stars or something? Can't we like use like a atomic clock? It would be much more precise and
Excellent question. Okay, so so you are right that today we have atomic clocks which are very accurate. When the origin of time came, okay, almost 2 centuries back, when the sort of timekeeping started becoming more precise, the highest precision was in terms of the sun. Okay, and it was the astronomical objects which gave you very accurate time. So most of the last century, the timekeeping has been astronomical. We didn't have atomic clocks in those days. Okay, in fact, the quantum mechanics got discovered only in 1930s. So before 1930s, the concept of the atomic clock itself was not there. It's only when the quantum mechanics got discovered that you found atomic transitions which could be actually defined very accurately in terms of wavelengths. And when you define the terms of wavelength to a large precision, you are able to convert it into time. Okay. So the best atomic clocks only came about in 50s and 60s. So it's around that time that the timekeeping went into atomic clocks and has remained in atomic clocks. So our time nowadays is not defined astronomically. Our current civil time is defined by atomic clocks, which used to be cesium clocks, which are 1 part in 13 accurate. Slowly from cesium, people have moved to iron fountain and iron trap clocks. And today you have experimental clocks, which are 1 part in 18 accurate. Okay. And no way the Earth's rotation or any other rotation is able to rival this kind of short-term stability. So today the time is on the atomic clock, but that leads to all kind of problems. For example, the Earth's rotation slows as a function of time. So if your watch is synchronized to an atomic clock, then slowly your day will start shifting with respect to the noon, and at some point of time you may actually have midday in the night and so on. So what is done is that the atomic clocks are adjusted to match with the rotation of the earth so that human beings can live the way they have lived all these years. Okay. So, but you are right that today the timekeeping is not done by astronomy, it is done by atomic clocks and will continue to be done by atomic clock in the near future.
Okay, sir. Thank you.
Okay, so the other thing which I thought I'll spend a little bit of time is how do you actually analyze the data? Now, you have been given a worksheet on some radio astronomy data using OT radio telescope. I think Desh has given you some exercise. So maybe I'll stop sharing here. Prakash, is it possible to display that data somewhere?
Prakash has like went to washroom, so
Okay. So this is Jamir, right?
yeah, I'm saying.
So Jamir, is it possible to show that data somewhere or no?
Just a second, I will check.
I will stop sharing.
So this pulsar data, right?
Yeah, the OT data, which I think Desh was showing, has given as a worksheet for everybody to do. For that matter, any student can also put it up, okay? Because they will be having the data, right? So any of you, please raise your hand if you have the data with you ready to display. You know how to raise your hand, right? In the participant box, just go and say raise hand. Does any of the student have? Okay. So Geetanjali, can you share a screenshot of that data?
I'll share my, if I'm allowed to share my screen, I can share how it looks
I
on Google Colab.
I think you may be allowed to. Jamir, can she share the screen?
Yeah, she can.
Yeah. So yeah, please go ahead.
Yeah, I have opened it. So shall I share or?
Oh, okay.
That's okay.
You can share.
Yeah. Then it's easier for you to share.
Then you can share. Yeah.
Sure. Just a second. So can you see my screen?
Yes. So, okay, this is the notebook. Is it possible to plot the data somehow?
Just a second, I will check.
It must be there in the notebook somewhere. There must be a plot or something. No, this is only printing.
So can you plot the? Yeah, BCJ is asking to plot.
Plot what?
The ORT data. Can you plot?
Oh, I can show you.
Yeah, just a second. Prakash is here. He's plotting the data.
So you can just. So this data is what is spectral data or what? What? Raw voltage data. Okay. So it doesn't have any frequency resolution, right? It's so maybe you can plot one of the channels of the Fourier transform. Okay, so you can try that out, and we'll come back to it when you are ready. Okay. So unless Geetanjali or any of the students have actually done it, have any one of you actually done the Fourier transform and plotted it just for fun's sake?
I have not reached Fourier transform, but I have plotted the distribution. So Gaussian, I can show you.
Okay, that is also not bad. I can probably take over from there. Yeah, so maybe Prakash, you can allow Gitanjali to share the screen. Okay, great. Okay. So, that's great. So this is just the basic voltage data. Now, just go to the voltage time series. Okay, the earlier one. Okay. So this is what typically the data looks like. Okay. Now, obviously, there is a pulsar hiding somewhere in that data. That's what I believe. So this is the Vela data, Prakash?
Yes.
Okay. So there should be a pulsar hiding somewhere in that data. Okay. So typically you get something like this coming out of a telescope. Now you want to extract information out of it. Okay. So there are two components here. One is the noise and the other one is the signal. Okay. For astronomy, the signal is also noise. Okay. There is no difference between, so it's one type of noise to the another type of noise. And I think Desh must have covered this to some extent, that the reason why astronomical signal is also noise, okay, because many of the sources are thermal in nature, so you will have a thermal noise. Some of the sources are non-thermal, but still it represents a noise. So the brightness of the source with the bright point which you see is just like any other noise. Okay, and of course the instrument, which is the radio telescope, also produces a noise. So when you are looking at a blank part of the sky, you will mostly see the noise produced in your radio telescope, and there would be no signal. But when you are looking at a bright part of the sky, or you are looking at a source, at a star, like a radio pulsar or something, you would not only see the telescope noise, superposed on that telescope noise, you would see an additional component of noise, which is what astronomers call as signal. Okay. So this is something, especially for the students who are from engineering background and maybe electronics background, the connotation of signal and noise in astronomy is different from the connotation of signal and noise as far as the communication engineers are concerned. Okay. So that's one of the things. Now, so you need to actually want to extract signal out of that. Now, here there is a pulsar, and you have had a lecture on pulsars by Devabrati, I think, and she must have explained to you that pulsars are neutron stars which are highly magnetized and which are rotating, and they emit their emission in the form of beam which is anchored to their poles. So every time the star rotates, the pole comes once in the rotation time in your line of sight, and you see a bright flash of light. Okay. So the signal which is coming from the pulsar is not continuously there. Okay. It is periodic. It comes once in the rotation cycle of the star. Okay. And it appears like a pulse. That is why these sources were known as pulsating radio sources, or pulsars. Okay. That's the full form of pulsars. So it is periodic, and it so happens that these stars are neutron stars, which are very massive and which are very compact. They have very large moment of inertia, about 10 to the power 45 grams centimeter square. And they are rotating, they are very compact with a diameter of about 10 kilometer or so. So typically maybe 1/5 or 1/10 of the national capital region, or say 1/5 of a large city like Mumbai or Chennai. Okay. So looking at that scale, you can imagine that they are very, very compact stars. And within this compact star, you have a mass which is about 1.5 times the mass of our sun. Okay. So the densities are very large and the moment of inertia is extremely large. And they rotate fairly rapidly, typically rotation periods of the order of a second. So the whole star rotates in a second. Contrast that with the rotation of the Earth, which takes 24 hours or about 86,400 seconds longer than the rotation of a pulsar. Okay. So because of this, the rotational kinetic energy, which is just the moment of inertia into omega square, I omega square, is extremely large. And because the rotational kinetic energy is so large, it is very difficult to slow down these stars. In other words, the rotation of these stars is very, very stable, is ultra stable. And that ultra stable rotation means that the periodic pulse signal which we see are also highly periodic. Okay. So even though what you see on the screen is pure noise, okay, and you can actually look at its statistical characteristics, which is what I think Gitanjali has plotted. So if you can go down in the histogram, that is how it looks like. Okay. This is the familiar normal distribution curve, which has a mean of about 0 and a standard deviation of about 40 or 50. So it's basically noise. But if you have a pulsar in this signal, it is periodic. So if you can do a harmonic analysis of this signal, you should be able to collect the power, the noise power, which corresponds to the power coming from the pulsar in a Fourier transform bin, which is corresponding to the inverse of the period of the pulsar. On the other hand, the noise which is introduced by the telescope is completely white. White noise means noise which has a frequency content from 0 to infinite frequencies. That is, the amplitude of the all frequencies is identical. So since the telescope noise is white with the identical amplitude of all frequencies, the pulsar signal will stand out on that. And I think that is what the exercise in this worksheet is all about. Okay. So one is doing a harmonic analysis, and harmonic analysis means taking a Fourier transform. And a computationally efficient way of taking a Fourier transform is called as fast Fourier transform. So that is what you will do in Python. You'll use the Python function FFT to actually get the fast Fourier transform. Can somebody tell me what will you get? So you have a voltage data. When you take a Fourier transform of that, what are you likely to get? So your current data is a real data. Once you've taken a Fourier transform, what kind of data will you get? Can anyone answer that question?
We'll get a spectrum.
Yeah, you'll get a spectrum. But what would be the nature of the numbers in that spectrum?
So the x-axis will be the frequency range and the y will be the gain for the particular frequency or the voltage levels for a particular frequency.
No, so that is only half of the answer. There is something else you should get.
Oh, it's a imaginary number.
Right. So you have a, what kind of transform is a Fourier transform?
Linear.
Yeah. No, it's a complex transform, right? So if you have a real signal, you will end up with a complex spectrum. Right?
So we will have a phase and an amplitude.
Yes, you'll have a phase and an amplitude. So you need both the parts there.
Both.
Also, there is some other property of the spectrum which you should see. What other property of the spectrum which you see?
See the dispersion delay for the...
No, that's, we are going to the pulsar. I'm just saying, suppose there is no pulsar, it was only telescope noise. Then also you will have a Fourier transform, right? And which will have a amplitude and a phase. But what other things? So this is something to do, this is nothing to do with astronomy. This is something to do with Fourier transform. I'm just trying to see how much has seeped in. Okay. Desh has covered it extensively in his lectures, Fourier transform. But how much of that you have absorbed is what I'm just trying to see.
So if the distribution here is Gaussian, it's going to be a Gaussian even in the Fourier space.
That is one thing, but I'm talking even more basic than that. It's simply coming from the Fourier transform properties.
Probably periodic.
So I said that Fourier transform is a complex transform, right? And so what kind of properties a transform like that has? So let's say there are 1024 points which you have taken a Fourier transform. How many frequencies you will get in spectrum?
The same number.
Think a little bit. Okay, let me rephrase my question. How many unique frequencies you will get in your spectrum?
The half of the total points.
Why? Your answer is correct. Your answer is correct, but you justify that.
So as it is complex, it would be positive and negative. So we would be taking either a positive part or a negative part.
Okay.
Or we'll do a Nyquist sampling. So
okay, both the answers are correct to some extent. Okay. You will take either positive or negative, you said, but that makes an assumption that the positive frequencies are identical to negative frequencies. So is that correct for a transform like that?
Yes, sir.
Right. So Fourier transform has what is known as Hermitian symmetry. Okay. So that symmetry properties of the Fourier transform ensures that the positive and negative frequencies will be identical. So you can throw away half of those 1024 points. The unique points are only 512. And the other physical way of understanding is what somebody else answered, that there is something called Nyquist. What is Nyquist frequency?
Balchand, you're presuming real data, right?
Yes, I'm presuming real. Oh, that's Desh kya? Okay.
Yeah. So it's
Desh
worth insisting on that, that it's only for the real data that it's Hermitian symmetry.
Yes, yes.
but then Desh sir also said it's for real and asymmetrical data. So what was that thing?
No, the data which you plotted above seems to be the real data, right? If you just go back to the earlier data, I thought it is only one-time series. Yeah, this is real data, right?
Yes.
So.
And so what is meant by asymmetrical? Meaning you said real and asymmetrical.
Desh can explain. I don't know the context. Yeah.
No. Yeah. All that I said is if you have real data, then the Fourier transform will have Hermitian symmetry. And that is where what Balchand was pointing out, that the other half on the negative side of frequencies is not having any independent information. And so it can be thrown away.
Okay. And if it is an imaginary data, then it will be an anti-Hermitian. So
if it is a complex data, then it is, then it is different. Okay. In fact, the two transforms are symmetrical in two domains. So you can have a complex time series being fed and you will get a real spectrum.
Then you might get even one-sided spectrum.
Yes.
Okay.
And for which the Nyquist criteria is different.
Correct. And that is also implied in astronomy. In fact, it is getting more and more implied when you do RF sampling, direct digitization. Okay, so these are all things which are very much used in radio astronomy. Okay, so it's good to understand those concepts. Anyway, so as I said, that all the power for the pulsar will then get collected in one of these frequency bands, and that will rise above the noise. If you had no pulsar signal, if you just had noise, telescope noise, what would be the amplitude in the spectrum? Is it related with some Fourier transform theorem? Does anyone know that theorem? There is a theorem which relates the power in one domain to the power in another domain.
If we compute the power in both domains, that would be
Parseval's theorem.
Parseval's theorem. Correct. So you could actually do this experiment or you could do this calculation. You could work out what would be the typical power distribution only in the noise versus the power collected in one frequency bin as far as the pulsar is concerned, and see how that makes it easier for you to extract the pulsar signal from this apparently noise-like looking signal which is sort of shown here. Okay. So I think that these are some of the things which I just wanted to sort of point out. But other than that, now let's say if you have got the pulsar, okay, and this is I don't know. So this is 1,000 samples. Is the x-axis in seconds or it is in
No, I have just plotted a part of it because
part of that? Okay.
yeah, I just
No.
plotted a small part. There is roughly it's much more than this.
Yeah. So 32 nanosecond is one sample.
Yeah.
Okay.
So roughly.
Yeah.
So this is the
Correct.
other
Correct.
one.
So your data, I can tell you how big your data was. Just if you go down, what was the y-axis? Yeah. So it's about 10 to the power 4.
Yeah.
So 32 nanoseconds. So it's less than a second of data actually. Okay, maybe there is no pulse also in this.
The entire data are only 1 second.
Yeah. So this must be a fraction of second looking at the sampling time which UT sort of operates on. So so to get the pulse, you will have to, and since they said 1 second of data, so there will be a certain number of pulses in this. So you have to choose the right place where the pulse is, okay, to be able to see how it looks without the things. Okay. Now, why are we taking Fourier transform of this? Can anyone, other than the fact that there is a periodicity which is there, there's another reason why we are taking a Fourier transform of this data. Can anyone say anything about that? No, I don't expect an answer here. I'm just trying to figure out if somebody has an answer.
So the pulses, like for a pulsar, will be symmetric. I mean, it will be periodic. So if we take a Fourier transform, like so, if there is any sinusoidal wave lying inside the data, like we can get the frequency of the data and separate that.
That is what we discussed, but that's not the only reason why we are taking a Fourier transform. There's another reason.
I think his question is essentially, why couldn't we take just the power as a function of time?
Yes.
For the entire band, why do we need to analyze the spectral information in detail?
We need the phase information and how it is delaying or.
Why do we need the phase? No, your answer is correct, but why do we need the phase information?
So it's an electromagnetic wave, so I mean, you need, that's why.
Something related to rotation.
No. Okay. So that's fine. So can you unshare this? How much time we have, by the way? I think I have already beyond 1 hour. So Prakash, am I supposed to continue beyond 1 hour, or I can stop and maybe do it tomorrow? Yeah. No. So we were actually reaching a logical stop. Okay. Whatever I wanted to say next, I have already motivated to some extent. Okay. But what I will say next will require another 30 minutes. So I don't think, unless, I don't know, it depends on what you do after this. Okay. What's the next part of the program? Okay. No, so I think we should stop here, and maybe I can continue from where I'm leaving today to tomorrow, where I'll become more pulsar specific now. Okay, so is that fine? Okay, so so we will continue where we are. So just remember that we ended at a point where I asked you a question that given this time series, we can of course take a Fourier transform to find out the period of the pulsar, but there is another reason for taking the Fourier transform.